now that everybody has arrived. Hello. First I want to have a few comments about the homework. Some of you came to the office hours and pointed out to me the following things. So first, I believe I changed on the website that the deadline is not now, but at midnight tonight, so you have a little bit more time. Second, and so you can send me by email, that's been done in the past. The second is that students pointed out to me the following issues. They said that the question on matrix completion seems to be working fine. They told me that the data set of faces has 10 faces for each individual, and that they throw away some of the entries, and that it seems to be working generally fine. However, they run into trouble when applying it to, for example, for corrupted entries. Okay? So here are the things that I said to the students that came to office hours. First, remember that there are two aspects and two parameters that are important. One is the parameter lambda, which is the relative weight between the low rank part and the sparse part. And that parameter lambda is supposed to be 1 over the square root of the size of the image. When is the algorithm expected to work? As we saw from the theorems, it's expected to work when the low rank matrix is sufficiently low rank and the percentage of corruptions is sufficiently small. Okay. So what happens is that you have a database of images with maybe the dimension is a few thousand pixels for each image, but there are only 10 examples. So it's very likely that in fact maybe, and that's maybe my mistake, not telling you that 10 examples is not large enough, because typically the expected dimension for a data set like a data set of faces is at least 9. Okay. So 10 is maybe too little. So I think it's better that you actually use the whole database that I believe, depending on the case, it has either 28 different illumination conditions or 38. So I don't remember the exact details. I think for frontal poses it's supposed to be 38 different ones, but for other poses there are only 28 of them. So I would say try with more images beyond 10. That's my first suggestion. The second suggestion is, and reminder, is that there is a second parameter of the specific algorithm that we're using, which is applying ADMM to solve the low rank plus sparse problem. That ADMM method has a parameter beta, which is the parameter of the augmented Lagrangian. It's very important that if you look at the algorithm, the parameter beta is the same as the step size of the gradient descent. Okay. So usually when you implement a gradient descent algorithm, you have the freedom of choosing the step size. And in fact, in optimization, there are lots of strategies for choosing it. But in the particular case of ADMM, the step size has to be the same as the parameter. Okay. That parameter beta will affect the convergence. In fact, sometimes people vary that parameter, and sometimes they increase it. Okay. So you have a little bit of freedom. So what things can go wrong? First, the algorithm is not converging, or it's getting stuck, and things like that. Okay. So you vary the parameter beta to either accelerate it or make it slow. The problem you're solving is convex, so it is expected. The method has proofs of convergence, so it should converge. So sometimes, and I was told in fact that it actually did converge, and in 2 iterations, you said. And so that was too quick, and it didn't give the right solution. Maybe it gave the E being equal to 0. Okay. So what that means is that if the matrix is sufficiently low rank and the percentage of outliers is sufficiently small, why would you get an E equals 0 solution? That tells you probably that the lambda is too large, because it's penalizing the sparsity too much. Okay? So that's how you know you need to modify the parameters. So sure, the theorem is telling me that I need to use that number, but you would like to also get it to work, right? So you can modify it. So if the low rank part is 0, probably you want to increase the lambda. Okay, so those are extra things that you can play with. Okay, so that's one set of comments that I wanted to do. The other one, someone asked me, how do I evaluate the outlier part? Okay, so maybe I should write, right, so we are talking about, so everything I said in so far, maybe I should have, everything pertains to this algorithm. So that's what I was talking, and that's the lambda that I was talking. So for the outliers, we are doing the same, but it's plus lambda, and now it's the 2, 1 norm. Okay? So the way you determine what is an outlier is that, so xj is outlier if the norm of ej to norm is bigger than some threshold. What letter should I use? Maybe epsilon. Okay, that's the way you determine whether a point is an outlier or not. So the question as stated, I think you can read it, so in fact it's probably here. Maybe it's not perfectly complete. So this is problem 311, is that right? So I'm referring to this question about outlier detection. So it says report the percentage of correctly detected outliers. Okay? So what's going to happen is the following. You know what are inliers and what are outliers, because you as the user, as the programmer, have control of the data set in this particular case, right? So face images are inliers, the other ones are outliers. So you know the truth. Now you run the algorithm, you put some threshold in there, and that will generate outliers. What the algorithm generates need not coincide with the truth. So now you have to measure the agreements. And so in statistics, there is this notion of true positives, true negatives, and so on and so forth. Right? So if it truly is an outlier, was it detected an outlier? That's exactly what this agreement, right? The percentage of correctly detected outliers. But think about what will happen, right? If this epsilon that I choose is tiny, teeny, everything will be an outlier, right? If that epsilon is very large, nothing will be an outlier. So the error, or the percentage of correctly detected outlier, will vary with the choice of epsilon. And so what should happen really is, as I just said, if epsilon is very small, right? Let's be extreme. If epsilon was 0, and let me actually make it bigger than or equal to, just to make my point. If epsilon was 0, the algorithm would say that everything is an outlier, right? So by definition, they are correctly detected. Oh, it detected them all, but it detected more than it should have, right? So that means that it will probably do very well. So it will do 100% correct. But as the epsilon gets larger and larger, this will go down. So perhaps plotting this percentage as a function of the threshold is a better strategy, so that you see that maybe there is an ideal threshold from which you get 0 error. Right? Now, if you are a statistician, and many of you are from the AMS department, you know that this is just one side of the coin. Right? So it's not the correct measure to assess whether you're doing a good job, because you need to also compute the false positives, false negatives. In fact, what you should be doing is an ROC curve as a function of the threshold. For each value of the threshold, you will have some detection of what inliers and outliers are, and you plot both. You plot the ROC curve, and that will give you. So that's what is usually expected. Of course, here I've never taught anything of that, so I'm not asking you to do anything fancier or not do the statistically rigorous thing. So let me just modify that question as saying report the percentage of correctly detected outliers as a function of the outlier threshold. Okay, that, just to make it more precise. And I think I apologize that it's vague. As I told the students, once you're a professor, a few things become evident to you because you've seen them 100 times. And so you just write, and you forget that you were a student once, and the very first time it was not as easy to figure out what it was. So I'm sorry that it was incomplete. Okay? Are there any other questions regarding the homework beyond those? So, feel free to take more time. If you want to turn it in tomorrow at midnight, that's perfectly fine. Because I think these corrections are my fault really, so I'm happy to give an extension. Okay.
So, in most of the face recognition problems, the dimension is given from 1 to 10.
Yeah.
It should be 1 to 5. Shouldn't it be? Because the training set is half of the data set.
Yes.
So
but I think I'd like you to increase for these methods to work, you have to have the number of inliers needs to be much larger than the dimension of the subspace. Assume that typically the dimension should be 9. So I would say modify the questions so that they accommodate ideally the 28 examples that you have available. So don't, in a sense, answer the questions in a way that makes sense. Don't stick blindly to the protocol, which is done presumably by a professor who thinks of what it should be done but has not done the experiments himself directly. So feel free to do modifications. Okay. I mean, think about ultimately. My goal is not for you to blindly follow things. My goal is for you to actually learn, and I hope that by programming the algorithms, you've learned actually how they operate. And you've learned that there are parameters and that to make them work is a little bit harder than just writing the equations on the board. Okay, so that's the objective. So as soon as you've learned that, you don't need to, and the TAs here listening, you don't need to follow the recipe exactly. The idea is for you to demonstrate what the method is doing. Right? So if you're evaluating in a regime that makes complete no sense, that's probably not a good strategy. Okay. Any other questions? Okay. All right, so back to the lecture. So I wanted to remind everybody that we are looking at nonlinear dimensionality reduction. And the reason why we're looking at nonlinear dimensionality reduction was one motivation that I gave was this idea of applying PCA to phases from one individual in multiple poses. And by plotting the two-dimensional embedding, I convinced you that people, the different poses are all intermingled with each other. And the PCA was unable to discover that, say, one dimension is illumination and another dimension is color, for example. So we've been looking at, first we looked at kernel PCA, where we take the data, we embed it into a big space, and then we apply PCA to the embedded space. In the previous lecture, we covered two algorithms. One was, and maybe I should write it down here, multidimensional scaling. And the other one was LLE. And what was the philosophy of these algorithms? The philosophy was, can I map the input data, let me call it X, directly into that low-dimensional embedding? And can I do so in a way that I just preserve local geometric structure of the data? And I said at the beginning that's very vague. What does it mean to preserve local geometric structure? But then we made it more concrete, and we said that, for example, if 2 points are close in the original data set, they should be close in the low-dimensional embedding. The second thing I said was we want to do that potentially locally, not globally. And so much of the way in which these distances are preserved is just based on a nearest neighbor type of graph. We discussed multidimensional scaling, and we said that we formulated exactly that question and said, can we approximately preserve the local distances? We said, yes, we can write it down. It's an optimization problem, but it's non-convex. And then we said, can we preserve angles? Can we preserve dot products? And we said, yes, and we can do it in closed form. And so multidimensional scaling on dot products actually led just to PCA, in fact. So then we were disappointed because we said, well, it just gives PCA. But then I said, it gives PCA if you preserve all dot products between all data points, but if you make it local, then it does nonlinear transfer. But then it was no longer closed form. So that was the key motivation for local linear embedding, which is, can we have an algorithm that is based only on local neighborhoods, yet I can still lead to a convex problem? Okay. And so the way in which locally linear embedding operates is as follows. The first step is to express every point, xj, as a linear combination of other data points. Which other data points? It's written here that it's all of them, but the reality is that it's only its k nearest neighbors. So that's why the first step of the algorithm is, given every data point xj, find its k nearest neighbors. The second step is express a data point as a linear combination of its k nearest neighbors. And that's why there is this constraint that the coefficient is 0 if xi is not a k nearest neighbor of xj. We went through the calculations, and we demonstrated that the optimal solution to this problem can be computed in closed form. This Cj vector that is here, it is simply the following: Ci1j, Cij, j. So this is a vector in Rk. Okay. So this is the vector of coefficients for the jth data point, of the connections of it with each one of its k nearest neighbors. So that's why it's a vector of dimension k. Okay? And the optimal solution is obtained as follows. First, you compute this so-called Gramian matrix. What is the Gramian matrix? It's the matrix of dot products. I am the data point j. I'm connected to this guy and to this guy. Okay? I compute all pairs of dot products among my k nearest neighbors. Okay? So it's effectively almost like finding the tangent. It's really, I motivated it. The manifold is being approximated locally by finding the tangent plane or the tangent space at the point xj. This matrix of all dot products is sort of the matrix of all dot product between all tangent vectors, because xi minus xj is an approximate tangent vector. Okay? So it's not maybe illustrated in this picture, but just imagine that around one data point there is a tangent vector, and so this is just the vectors from xj to each one of my neighbors, so that's an approximation for the tangent. So this Gramian matrix effectively captures the local geometry. And so as a matrix, this matrix is k by k. And now all we need to do is to solve a linear system, so G inverse times 1 is all what's needed. And this is normalized because I forgot one constraint. We also have the constraint that the coefficients must add up to 1. The sum of the Cij equal to 1, and this is the sum I equal to 1. That's an extra constraint that I forgot. Because what the algorithm is doing is express the point as an affine combination of its neighbors, effectively. Right? This is the summary of the previous lecture. I did the calculations, I explained why. And now we are left with the next step. So the next step is, I already in fact, if you think of this picture, right, what I've just done is taken the original data set, expressed it in terms of itself to produce a matrix C. That's what it did. So it was just capturing the local geometry. So the second step is, now that I know how the points relate to each other up there in the manifold, I want them to go down. And so that's what the third step is, which is find the low-dimensional representation. So minimize with respect to y. And the way it's done is really the same objective. And then xj minus the sum, actually I should now write yj, sum of cij yj, and 2 squared. So I'm going to actually use the same identical objective as I had before, but now I'm going to keep the coefficients constant, and I'm going to try to find the low-dimensional representation. This is I equals 1. So in other words, this is really a method that is in the same spirit I mentioned at the beginning. Try to find a low-dimensional representation that preserves the local geometry. What does that mean concretely here? Local geometry is represented by this C matrix. The geometry is captured by local linear combinations. That is being preserved because I keep it there without modification. And now I try to find these vectors y that are approximate linear combinations of each other with the coefficients being fixed. Now, the issue is that the global optimum for this problem, as written, is y equals 0, right? Because if y is 0, then the objective is 0. And I want to prevent that from happening. So a classical way, and this is what we have always used, is that we require the matrix y to be, matrix y is supposed to be d by m. So we require that matrix to be full rank. So one way to do it is require the rank to be d. But that's usually not great because the rank constraint is sort of very non-convex, right? It's nasty. We don't like rank constraints usually. So we usually like this matrix to be orthogonal, and that's what we did in the case of PCA. It is still a non-convex problem, but we've sort of gotten used to this idea that quadratic problems with orthogonality constraints, even though non-convex, the eigenvalues and eigenvectors show up all the time. So I'm sort of a little bit hopeful that things will work out. The other thing that we like to add to these low-dimensional representations is that we want them to be centered. So we want the sum of the y's to be 0. But we already know how to do that. Is y times y is equal to 0. So this is vector dimension. Okay. So I'm just adding these two extra constraints that will prevent, ideally, the 0 solution. So the next question is, how do we solve this optimization problem? Okay, and that's what I will address today. So, so I'm going to just write down the solution for now, because the optimal solution for it is actually a special case of the problem we're going to discuss next for Laplacian Eigenmaps. So let me just write down the solution. But the solution would be the following. So solution. So let L be equal to I minus C transpose I minus C, which is a matrix that is n by n. let y is equal to y. This is d by n. Okay. So I'm going to take the y matrix that I'm trying to compute, and I'm going to discuss the rows of it. So then, y sub I is equal to the I plus first eigenvector of L. That's what the solution is. Okay? And I will prove this, and I'll keep it here in the board, but I'll prove this as part of the next method that I'm going to talk about, which will become, this will become a special case of that. Okay. Just to point out two things. First, what does the method do at the end of the day? How easy is it to implement and how is it done? It really consists of 3 steps. The first one is find k nearest neighbors. The second one is solve a quadratic problem, but in fact it has a closed form solution. And in fact, the size of that problem is relatively small because it depends on the number of nearest neighbors. Okay. And the number of nearest neighbors, we had said it needs to be above the dimension of the manifold, but it doesn't need to be very, very large. So effectively, you need to solve n problems of dimension k when you're solving that. So the largest problem is this one, because you've got an n by n matrix to worry about. In that matrix, you need to compute the eigenvectors. But it's sort of the typical thing we do in PCA. So the gist of it is that the complexity of this nonlinear dimensional array reduction in terms of computation is not a lot more than doing PCA. Okay. So it's the most complex part is computing these eigenvectors of this matrix. We're going to know in a minute, but I'm going to call it the Laplacian matrix. But the size is really the size of the data, and you just need to compute d eigenvectors from it. The second point I wanted to make is that here's I and here's I plus firsts. Okay? So unlike what we usually do, PCA was always the top d eigenvectors of the matrix. Okay? In fact, I should have said here, I should have added the word bottom. Okay, so what we're going to be using here is not the top eigenvectors, but the bottom eigenvectors. So the one corresponding to the smallest eigenvalues. And the important observation is not the bottom d of them. It goes effectively from the second to the d plus first. Okay? So the first, the smallest eigenvector is going to be disregarded. Okay? And the reason it's going to be disregarded, I'm going to prove it in a minute, but I want to explain. So, so first eigenvector is disregarded. So that's the important observation. The reason, and I'm going to prove that in a minute, is that L times 1 is 0. So the eigenvector corresponding to the smallest eigenvalue is the vector, the constant vector. Okay? And why that is a bad thing and all that, I'll explain next. Okay, so I just wanted to show, though, that the algorithm already improves. And let me show here the picture of what happens with the same data set we had before. Okay? So now we take the face images, 4 different poses, and we have 20 subjects under those 4 poses and 64 different illumination conditions. So look at what happened before. All of the colors were all intermingled. Now what you can see is clearly, it's not perfect, right? But clearly the y-axis corresponds to different poses, right? While the x-axis corresponds to changes in illumination. Like the pictures on the leftmost part are darker on the left, and the ones on the right are darker on the right. Okay? Of course, this is not all the dimensions, because again, you could have illuminations up and down. So you would really need to do a plot in R3, but the key idea is that this did capture fairly well the fact that you have a nonlinear manifold. It's no longer a linear subspace, and now it's sort of almost order them vertically according to the pose. And that's the result of this algorithm. So let me move to the next algorithm, which is called Laplacian Eigenmaps. So the philosophy behind this algorithm is sort of the same philosophy we've had so far. I have a high-dimensional data set, or data on a manifold, and I would like to preserve local neighborhoods, local geometric structure. But the way in which it's going to be preserved is in a different way. So the first step is the same as before, which is to find the k nearest neighbors. But the second step is the one that is done differently, and in fact, it almost integrates step 2 and 3 from LLE into a single step. And the idea is as follows. Suppose that I wanted to preserve directly the pairwise distance. Right, so I'm going to minimize the sum of pairwise distances. So, just for comparison, I'm going to write here the multidimensional scaling. What we did in multidimensional scaling was to say, I have a priori the distance between xi and xj that I can compute. And I would like to approximate it like the distance between yi and yj, 2 squared. And I said, we're going to sum over all i's and j's. That was multidimensional scaling. It was compute the distances on the original manifold, compare those distances with the distances in the low-dimensional embedding, and try to find a low-dimensional embedding that best approximates the distance. So that was clean. It was perfectly what we said philosophically, trying to preserve the distances. Here, this is done in an indirect manner. So what we're going to do is that we're going to put a weight in there. Okay? And for example, for the sake of concreteness, I'm going to define what that weight is. So let me make it here e to the minus xi minus xj squared divided, say, by 2 sigma squared. Okay. And let's try to compare the philosophy of these two methods. And I repeat, here was compute your distances in the ambient space, compare them to the distances in the low-dimensional space, and find the low-dimensional representation such that those distances are preserved. But it had the caveat that by summing over all possible i's and j's, I was trying to preserve all distances. And we went in the last class trying to argue that's not a great thing, really, sometimes. It's better to just preserve local distances. So maybe I'm going to sum over I being a neighbor of j, and now here I sum over all j's. That's what we did last time. So let's compare that to what's done here. Here, what happens if xi, if the distance between xi and xj is small? If xi and xj are close to each other, then what's going to happen is that this wij is going to be approximately equal to 1. Okay. on the other hand, if the distance between point xi and xj is large, then wij is going to be nearly equal to 0. All right. So let's think in terms of the objective function now. Okay. If it were the case, I'm not saying it is exactly, but if it were the case that wij was equal to 0, okay, does the algorithm care how far apart yj and yi are or not? Because what is this? This is really saying find a low-dimensional representation that minimizes a weighted sum of pairwise distances. Okay? Obviously, you're going to tell me y equals 0. We do a pretty good job, right? So obviously, we're going to prevent that, perhaps by saying that the same thing we did before. Do I want that? No, actually, it's the other way around, right? Y transpose needs to be in it. Did I do that before, or do I need to correct it? Yeah, I did it correct. Good. Okay, so forget about the degenerate case where y is 0, but this is really penalizes the sum of pairwise distances squared. Okay, but it gives a different penalty to each pairwise distance. So all I'm trying to argue is if the penalty, so this wij is really the costs that you pay for that pairwise distance. So if that cost is 0, if wij is 0, you can let the distance between these two guys be whatever. So it's like these 2 points are free to be as far apart as they want. In fact, the algorithm does not care how far apart they are. Second, because the weights as constructed have to be between 0 and 1, when the weight is equal to 1, that's the largest weight. So automatically, the algorithm will penalize pairwise distances, but it will penalize a lot the pairwise distances for points that are very close to me, and it will not care too much for points that are far apart. But it does so in sort of a smooth way, right? And so it's, instead of me having to necessarily specify the network and say the neighbors, and say which distances I care to preserve and which distances I don't care, this is done via this Gaussian that effectively just looks at the distance, and nearby points have a large weight. So it will care in a small neighborhood. Yes?
So why are we computing the nearest neighbors to begin with?
Because, okay, great point. There are lots of variants. One possibility is to do that, but in fact, what is typically done is that you do it like that. If I, j are k nearest neighbors, and 0 otherwise. Thank you for the question. Why do we do that? At the end of the day, we do that because in practice, and I think you can already guess from here, n might be very, very, very large. And so if lots of entries of that Laplacian matrix L are 0, then the matrix is very sparse. And I can exploit numerical linear algebra to compute those eigenvectors in a much more efficient manner. And so because in between 10 to the minus 10 and 0, it will have a little effect on what the eigenvectors are, we really like to set them to 0 when they're far. So that's the only reason why you compute the k-nearest neighbors. Now, of course, you're going to tell me, well, there is also this sigma parameter, and there is a trade-off between sigma and k, and that's obviously true. If that sigma is tiny t, then almost all weights are 0. If that sigma is very large, then I connect myself to everybody. But by putting the k on top of it, I have more flexibility. I can choose the sigma to be larger, and maybe make a mistake of choosing it too large, but the k will compensate. But anyhow, I'm still sort of just at the intuitive level by simply saying, what does this algorithm do then? What this algorithm do is that it wants points I and j to be very close to each other, if points xi and xj are closed. So in other words, the conclusion from all of this is that if xi, or if the distance between xi and xj is small, what this algorithm is going to try to do is that the distance between yi and yj should be small. Now, if the distance between xi and xj is large, then the algorithm doesn't care. Okay. So implicitly and in a different way, the algorithm is trying to preserve, not preserve directly the distances, but it's really trying to preserve these local neighborhoods. In a sense, all the algorithm at the end of the day they're saying is, if xi and xj were neighbors originally, in the original manifold, you want them to be neighbors once they are projected. And you want their distance not to be too far. That's all it says. Okay, so what I'm going to show now is that the objective function, let me call this function f of y. So the first observation is that f of y is equal to x times the trace of L times y transpose something. Okay, maybe once I do the calculations I will double check what I'm writing. Where L is equal to d minus w, and d is diagonal with entry dii, where dii is equal to the sum of wij over j. So that's what I would like to prove now. That's a little tiny lemma, but I can rewrite the objective function as such.
So this L is not the same as that
No,
one?
it's a different one.
Okay.
That's the L of LLE. That is the L of L. Okay, so let's go through the calculation. So I'll start with the sum over I and j of wij, yi minus yj squared is equal to the sum wij of yi squared minus 2 yi transpose yj plus yj squared. Right? I've just expanded the objective, sum of the squares, so not too much really. Sum over I and j. And so for the first one, I get sum over I. Here. So it's equal to the sum. Sum over j of the sum over I of, no, I don't do I outside, it's the other way around. So this is the sum over I of yi squared times the sum over j of wij. Agreed? That that's the first term? Yes? No? Right? So, this is the sum over j of wij. sum over j of wij. So this is dii. So this is the sum over I of yi squared dii. Okay? Plus, so that was the first term, I'm done with that. I'm going to add now the last term. The last term is sum over j of yj squared. And now sum over I of wij. Agreed? Right? It's the same thing, it's just that the I and j are changed. Correct? So, I hope you agree with me that this quantity here, well, the w is symmetric, right? Because it depends just on the pairwise distances. So the w is a symmetric matrix, that's a key property. So this will become, is the same, it's just that I'm summing over the other index, but this will become djj. Agreed? Correct? But now that you've looked at it, right, once you look at the first term and you look at the second term, they are the same. It's just that one has a j and the other one has an I. But that's just the mu index that I'm summing over, right? So the first and the second term here are actually the same, and it gets to be 2 times. Okay? Minus the middle term, and the middle term is 2 times sum wij yi transpose yj. Okay. And this is summing over both I and j. So if I add that here, it's minus 2 times sum over I and j of wij yi transpose yj. Okay? So, if this yi and this yj were not vectors, right? If this yi and yj were not vectors, but they were scalars, what is this? Right? Forget about the transpose, these are all scalars. This would be the sum of yi, wij, yj. Sum over all i's and j's. What is that? I go back to linear algebra and I say, what is y transpose w? Why? If I spell it out, don't we all agree that this is sum of yi, wij, yj? Right? Just write it down. That's what you get. Okay? So that is for a single vector here, and this vector is a vector of dimension n if this matrix is n by n. Okay? Alright? So, look at this equation. All what I'm trying to say now is that how do I expand this now to the case of a matrix? If this y were to be a matrix right now, this will be my y transpose and this will become my y. Right? Instead of the vector case, I have a matrix case now. Okay? If I actually take the trace of this, what I get is exactly the sum of the y I transpose yj wij. Okay. Do you believe me, or do you want me to do that calculation? So let's try it. Who wants me to do the calculation? No one. One. Who believes me? Okay, there is no joke. Okay, so that's exactly what's going on here. We've got trace of y, w, y transpose. Okay? Minus 2 times. And here is the same idea. The only thing is that I don't have the double summation. And the reason I don't have the double summation is simply because instead of dij, I have dii, so I only have the diagonal part, right? So the same thing happens. There is no difference, but because the matrix is diagonal, I just get that. But it's the same idea, it's the same principle, there is no difference. So now that I can put these two things together, this is the same thing as the 2 times the trace of y, d minus w, y. Transpose. And that d minus w is my Laplacian. And so going back to my little lemma to see whether I was right or wrong, well, let me do a permutation here. Right? So this is y there and L in there. Okay, so the summary of everything is the following. The Laplacian Eigenmaps sort of merges the last 2 steps in a single one. Directly, I want to compute y. The objective function, all I've done in this first step is to convert it from minimizing the sum of weighted pairwise distances, that was the original objective, with weights w, to a, in fact, you know all what I've done really. Do you agree that the original problem is quadratic in y? Do you agree that it's a quadratic or not? I hope you can see that it only has y squares, and right? So any quadratic can always be written as vector, matrix, vector. So all what this entire calculation does is exactly do it matrix. So, well, now it becomes that's the variable, the matrix of the quadratic, and the other variable. So it's just rewriting the quadratic into matrix form. That's all what I've done so far. But once that's in place, I can solve the optimization problem more easily, because now what I'm going to do is minimize the trace of y, L, okay, subject to constraints. And what constraints do we want? And I think I almost eliminated them. Oh, there. Okay, they're at the top. Now I see. I want the matrix Y to be non-zero, and I want the representation to be centered. Okay. These guys, the guy who proposed this is a paper from 2002, by the way. We moved 2 years. LLE was 2000. Laplacian Eigenmaps is 2002. So all of this manifold learning was super popular from 2000 to 2005. So these guys did a tiny modification to the constraints. So the way they wrote the constraint is y times b times 1 is equal to 0. And y times d times y transpose is equal to a. What does that mean? What modification that this entitled? Is it a major modification or not? And why is it that? So this one is very easy to interpret. In fact, both of them are fairly easy to interpret. If you think about it, the matrix Y the matrix Y is D by N, right? And the other matrix is diagonal, so it's D11, DNN, right? So D11 will multiply the first data point. D22 will multiply the second data point. So all what this is entirely equivalent to saying that Y tilde times Y is 0, where what is Y tilde is simply the data point times D11, the data point times D22, the data point times DNN. So is it a major change? Instead of requiring the low-dimensional representation to be centered, it requires the scaled low-dimensional representation to be centered. Not a big, so it's just making a little bit of a change of coordinates, if you wish. But then you would ask, why do I want to scale the representation? What is the purpose for that? What is the main reason? So the main reason is explained in the appendix to chapter 4. And I'm not going to go into the details, so I just want to spend 1 minute on the intuition. Okay. The main reason is because this paper makes a connection with manifolds and geometry, and what really is going on is effectively the following. In theory, we've got a manifold. In theory, for every pair of points, I have a real notion of a distance and a real notion of a geodesic. And in theory, I am trying to find what is called a continuous embedding. So if I have the manifold as a continuum and I'm trying to do the mapping to a Euclidean space, right? I should be able to do it for any point in the manifold. Okay? So what does it mean for a representation to be centered if now the representation is a continuous representation? Instead of the average of the data points being 0, what really I would like is that the integral of the y's should be 0. That's what it really should be. So I would like the origin here to be at the center. That's what I'm trying to say. Okay? The thing is that instead of doing it in the continuum, we are doing it with a discrete set of points. And when we're doing it with a discrete set of points, we could ask the question, how do I discretize the continuous integral? Well, the continuous integral, the discretization of the integral will be approximated by the sum. Right? But the fact of the matter is that if you go back to Calculus 101 and you remember how you discretize, right? There is always a weight associated, right? Correct? Because you have to multiply, you divide your domain in little tiny pieces, but each piece gets a weight, which is the value of the function. Okay? Or if you do, I forget now, there is the other way that you discretize I forget the name now. So, all what's going on here is that there is the dy, dy. And so now the dy goes there, and that's exactly what that djj is there. Now you're going to ask me why the djj is the appropriate weight to be using. So let's think about it for a moment. What we have done is that we have taken the data point and we have connected it with a few neighbors, right? Suppose, and okay, I've done this with k nearest neighbors, and as a consequence, each point is connected to the same number of neighbors. But the weights are those exponentials, right? So, if my k nearest neighbors are very far, those weights are going to be small. If my k nearest neighbors are all very close to me, those weights are going to be larger. So in a sense, this, what is this djj? It's the sum of the weights to all of my neighbors. That's what it is. Right? So if I'm in a very dense region of the manifold with lots of sample data points, I give it larger weight. If I'm in a very sparse region, I'm going to give a smaller weight to that data point. So it's the same thing that you do when you compute integrals, right? Or in fact, when you integrate a probability density function, if you get lots of samples in that area, it's because the probability is higher, and so you give higher weight. That's exactly what is being done, and that's why they do this modification. Okay? Again, my explanation is very high level and very stupid. Just read the appendix if you're interested as to why and all that. But in summary, we have now this optimization problem subject to those two constraints. Once the problem is formulated, now we are back to the realm of optimization, and we know how to do that, right? So we're going to have the trace of y L y transpose. Now we need to add a Lagrange multiplier for each constraint. So let's say I do lambda transpose y d1, and then I need plus the trace of lambda times minus y y. Right? That's what we do. That's what we do with Lagrange multipliers. So now the next step is that we compute derivatives and set them to 0. I shouldn't use the L. I've got Lagrangian and Laplacian. So let me call this F. So, what is the derivative of a quadratic with respect to y? Right. It's going to be L times y transpose, yes? Okay. Probably to make the dimensions match, I probably should put a transpose there. Let me actually double check. So this is n by n. This is the y, I define it to be little g by n, so this is going to be n by n. So this is n by n. So we are in business. We've done the transpose as correct. Okay, then the derivative of this second term is going to be, okay, let's put the dimensions, that's what always saves me. So this is n by n. This is d by n. So this lambda transpose is 1 by d. Right? And this one vector is n by 1. So the derivative needs to be then d times 1 times lambda transpose. And I check it because now the dimensions should match. So this is n by n, this is n by 1, this is 1 by d. So everything stays to be n by d. And the last one should be should be. Move the lambda on the other side. D times y transpose. lambda is n by n. Am I right? No, something is wrong. Lambda should be d by d, so it should be on the other side. Lambda is d by d. Actually, let's, right. The constraint, as you see from the top, and it's also here, is a d by d constraint. So the lambda matrix that I'm putting here is d by d. So it needs to be then d y transpose. Say again?
2 L y transpose.
Yeah,
minus
of course.
Q.
So there's a 2 there and a 2 there, I guess. Yes. Okay. So, I'm running out of time. I only have 5 minutes left. I think we have done this many, many times in the past. What is it going to happen? Right? The affine term, the term in the middle, actually, this is the first time we did PCA with the affine term and we computed the derivatives. We were able to prove that the term with the middle with the extra constraint disappears. So the Lagrange multiplier for lambda is 0. Okay, now I don't remember how to do that, but presumably what we do is that we multiply, for example, by y, and so if we multiply by y, we get y times L times y transpose, right, with a 2. Then if I multiply by y, I get this. And so I know that as a consequence, one constraint that I get right away is that y d y transpose lambda, and a 2, that's one of the equations that I get. Should I do that? How do I prove that the lambda is 0? Probably I need to use the other one then. Probably I need to use this one. But y d y transpose is the identity, so in fact this is just lambda. Okay. What other thing can I do? I don't see anything else that I can do. Okay, I forgot, and I run out of time. So let me just tell you what is going to happen. What's going to happen is that you can prove that lambda is 0. So just believe me that. And therefore, what you get at the end is that this happens. D y transpose lambda. Okay? So, let me consider the special case. If D was the identity, of course it's not, but if D was the identity, what you get is L times Y transpose is equal to Y transpose lambda. Okay. What problem is that? L times x equals to L times y equals to lambda y. Eigenvalue problem. To show that it's an eigenvalue, I still need to show you that the lambda needs to be diagonal. But the arguments, we've made this before, right? The y is only true up to a rotation. If I rotate the y, okay? So I've done this proof many, many times at this point. So lambda is diagonal without loss of generality. So, as a consequence, the columns of Y transpose are eigenvectors of L. Which eigenvectors right now? Well, in PCA, at the very beginning of the class, we were maximizing the covariance, right? So that's how we ended up with finding eigenvectors that corresponds to the largest eigenvalues. Now, we are minimizing, right? The optimization problem here is minimize that quantity. So, as a consequence, I need to choose the smallest eigenvector. So, in principle, and I'm going to put a question mark, this should be the D smallest. Okay? But, here is the extra caveat. The extra caveat is the following. L times 1 is equal to 0. Why is it so? What is L times 1? Well, L times 1 really is the sum of L, I, J, well, the sum of L, I, J, right? The ith entry, in fact, maybe I should write it more formally, L times 1. The ith entry of it is nothing but the sum of L, I, J. Sum with respect to J, 1 to n, right? I've got a matrix, I multiply the vector of 1s, I get the sum of the columns. Okay, so I sum over the second entry. Good. But what was the Laplacian? Where was the Laplacian defined? Ah, here it is. Is D minus W. So this is the sum of D J J, if you wish, no, maybe D I I, minus W I J, right? The IJ entry of this L, well, actually, I need to be very careful, right? Because that is the diagonal matrix, so it could be 0 or not. So this is what? Or maybe I can just split it into the two terms. Right? Let me do that. This is the sum from 1 to n. So as a consequence, it will be the sum over j different from I of the Lij's plus the Lii. Therefore, it will be the sum j different from I of Wij with a minus sign, because L is equal to D minus W. So when I is different from J, Lij is minus Wij. And the Li term is Dii minus Wii. Right? So the ith entry is D minus W. All others are just the minus W. So, if you keep expanding that out, you get Dii, and what do I get here? Wii with a minus sign, and minus all the others. So this is just the sum of the Wij's, all of them. Right? But what is the sum of the Wij's? Oh, here it is. It's Dii. So this is equal to that, so this is 0. Okay, maybe I was really stupid. I shouldn't even have written it down. Because what I'm saying is, what happens if you take the matrix of weight and you multiply it with a 1? You sum all the weights, right? What is D? It's the sum of all the weights. So once you multiply, so D times 1 is the same as W times 1. Okay. Sorry. Bottom line is, the matrix L is positive semi-definite. It's symmetric, positive semi-definite. The eigenvalues of it are all non-negative. 0 is one of the eigenvalues, because what this proves, right, that this proves that 1 is an eigenvector corresponding to the 0 eigenvalue. So the smallest eigenvalue is 0. Okay. So if I choose the eigenvector once, I'm choosing a constant for that I should have been. So that, and now I go back to the extra constraint, right? The extra constraint, which I sort of eliminated, which is here, but I'm assuming this is the identity, right? Says effectively that I want the rows of y to be orthogonal to the vector of all ones, right? That is the extra constraint. So, what is the final conclusion? The final conclusion is that the columns of y transpose, which is the same as the rows of y, have to be eigenvectors of L that are orthogonal to the vector of all ones because of that constraint. Okay? I know that for a symmetric matrix, all of the eigenvectors can be chosen to be orthogonal to each other. And I know that the smallest eigenvector is the vector of all ones. So how do I select eigenvectors that are orthogonal to the vector of all ones? Well, all of the other ones, by constructions, have to be orthogonal to the vector of all ones, which is one of the eigenvectors. So the second, the third, the fourth, the d plus first are the ones that need to be chosen. Because they are the ones that correspond to the smallest eigenvalues, yet they are orthogonal to the vector of all ones. And being orthogonal to the vector of all ones is needed in order to get a centered representation. That's the summary, and that proves my original claim that is written here, that you need to get the bottom from the second to the d plus first. Okay. But I did all of that under this big if. Okay? If d was the, so in a sense, this provides the proof for the LLE, but not quite for the LE method. Okay. And I'll do that next class, but it's really a rescaling. It's a generalized eigenvalue problem as opposed to an eigenvalue. Okay? Actually, next Friday. So, summary, next Monday is the exam, 12 to 1:15 here. And the homework can be turned in tomorrow by midnight.